Is my screen visible?
Yes, sir. Yes, sir.
Yeah. So in my last session, I showed you how to create regular files, and also I described at length what really happens behind the scene when the files are created. Namely, the inode table structure is created in the kernel space, and all the data about the files, it's called metadata, is stored in this inode table. Now we have been creating regular files, and we also know that directory is also a file. So today we shall see how to create a directory file, and there is a API called as mkdir, where you specify the directory name and also mention the file permissions or the directory permissions. And if this returns 0, it means the directory will be created successfully. So you give a message directory created. And sometimes it may fail to create the directory. Maybe you don't have permission to create directory files in this folder. So that time you should say fail to create. Okay, so let's see what happens when I run this. Okay, so first thing is we need to compile this gcc mydear1.c minus it is md1. Okay, so if I say md, it's failed to create directory file. md1.c. Okay, so I think so there was already one mydear directory which it was refused to create the same again. So now if I see ls minus l, this mydear1 is created. Okay, now what is stored in this mydear? If I go to mydear1.c, sorry, mydear1, and if I do ls here, you don't see anything. Okay, but if I create a file, let's say hello.txt, and type something here, hello, this is a test file, and do a control Z. Now if you see ls minus l, it shows that file is created in that directory. Okay, now along with the name of the file, right, something more is stored in this directory file. So to know more about what is stored along with the name of the file, you have to give ls minus li. When I do this, you see one number comes up here, 12025. So this number is unique to every file. So this is nothing but your inode number. Okay, so I was telling you about inode. This is a number which is assigned to every file. If you go back to your previous directory, there are so many files here. Now if I do ls minus li here, every file which will have a unique inode number, as you can see here. Okay, you have unique inode number. Now how does this inode number is helpful to locate the file on the disk and get it in the memory and then do the processing? That is what you need to really understand very clearly. For that, I will take you to this diagram. Now, as I told you, whenever you create a directory and in that directory you create a file, let's say file1.txt, what you get is the inode number. Now, this inode number, this is just a number assigned by the system. How is this used to locate the address of the disk blocks on the file system? So, here is how the address of the inode is calculated. So inode table, as we know, it is a table in the kernel space. It will have a start address. Let us say some 8000 here. So start address is set by the kernel. Let us assume some address, and whatever inode number that we have here, 3056, that is taken. And inode structure has certain size. Let us say this takes some 40 bytes. So whatever that number that results, okay, so you have to multiply this 3056 with 40 and then add it to the base address, so that you get some, let's say 9156, something like this. Okay. It may be higher than this, some address like this. So this is the actual address where your file is stored on the disk. Okay. So here in the diagram, as you can see, you have only the file descriptor here. Whenever you open a file, you have a file descriptor and file read write permissions are shown here, and this is a pointer to the inode. Okay, so actually this pointer address is calculated using this formula. You take the inode number, multiply it with the inode size, and then take the inode base address and whatever value that comes, 91562. This is what it is, 91562. So this corresponds to the inode structure in the memory, and this is what is brought into the RAM, and this contains all the metadata about the file. Metadata means the data about the file, that is the mode in which you opened the file, how many hard links are there, who is the owner of the file, to which group he belongs, what is the size of the file, at what time the file was created. And then we have direct block addresses here, 12 of them. If you exhaust these 12 blocks, this will point to an indirect address block, okay, which in turn contains addresses to the actual data blocks on the disk. Okay, so we may have first level indirection, second level indirection, or third level indirection. So this is a good enough structure to accommodate file of any size. Now what actually is happening when you are creating a file is that this is the sequence that follows. You give a file name, it will make an entry into the directory file with the inode number. This inode number is used to calculate the inode address. So the inode structure is brought into the memory. An entry in the file table is done. Okay, and then the file descriptor is provided to you. Using this file descriptor, you will be referring to the file subsequently. Okay, so that is what you need to understand. And if you look at the actual inode structure, it would look something like this. It contains the inode number, the device on which the file resides, the mode in which you have opened the file, who is the owner of the file, what is the size of the file, at what time, the block pointers, reference count, and it might also have the locks. You might lock the file, okay, and what operations you are actually performing on the files. Okay. Now Unix supports many file systems. So file system defines the way the file actually gets stored on the system. So there are many different file systems. ext4 is the latest on Linux. There is XFS, there is NFS, there is procfs. Now anything related to the processes, if you want to store the data, it uses proc file system. This is very efficient when it comes to storing the process related data. Then there is a temporary file system which might be used for storing temporary files. Then there are device files. Now as I told you, the operating system has to interact with many devices. This could be your printer, it could be your keyboard, it could be device like hard disk, or your pen drive. All these are external devices that might be connected, or camera, whatever. Each one is treated as a device. Now in Unix, what is done is the devices are also treated like files. Okay, so that is one beautiful feature about Unix, that the devices are also treated like files. Just as you open a device, a regular file, you open a device file and start performing read and write. However, to interact with the devices, you require what are called as device drivers. So device drivers are programs which are installed inside the kernel, which will know exactly how to write to a printer if you have a device driver corresponding to the driver. Similarly, there is a specific device driver for the hard disk, specific for the pen drive, keyboard, etc. Because the nature of these devices are different. Like keyboard is a serial device, only one character goes at a time, whereas pen drive and hard disk are called as block devices. Okay. Similarly, camera could be a serial device or a block device. Printer is a serial device, one character at a time you are sending. Now, how do I create a device file? There is a command to do that. So, mknode is the command, and normally all device files are created in the /dev directory. Okay, you can give a name to the file, and then you mention whether it is a block device or a character device. So if you are, let's say, interacting with the hard disk, then you say B here. But if you want to create a keyboard, then it should be C. And there are two numbers here. These are called as major numbers and minor numbers. Now, one device driver might have many sub device functions. Okay, so in that case, the major device refers to the full driver, and within that driver, minor number refers to the actual device operations. Okay, so in that case, you require a minor number. So these two have to be specified when you want to create a device file. So let's see how to create a device file.
Sir, what is minor? Can you repeat, sir?
See, assume that you have a device driver, and this device driver has subparts. There could be a single device driver helping you to interact with more than one device. For example, you have a keyboard and also, let us say, printer. Both are serial devices, but you have only one device driver. So if it is one, you are actually using the device driver corresponding to the keyboard. If the minor number is 2, you are referring to the printer device driver. So this is the major number which refers to the device driver, and minor numbers refer to the sub devices. Okay. So you can create this device file here. You say mknode /dev/ you have to give some, let us say you want to create a keyboard. You can give any name and some major number like 9 and minor number like 2. Yeah. And you must mention what type of device it is, whether it is a character device or a block device. So when I do this, yeah, now normal users cannot create the device files. You require super user privileges, so you must prefix the command with sudo. Okay, so here it is asking for the super user password. Once you do, that device will be created. So if I say ls/dev, you will see that keyboard will be present somewhere. Or if I do ls/, see that device file is created. And if I give ls -l here, you will see that it is a character device which has read write permission, and it has a major number 9 and minor number 2. Okay, of course you have to write a device driver and install that, only then you will be able to perform read and write to this keyboard. Okay, so using mknode command you can create a device file.
So one is character driven, other one is what?
Block device.
Block.
Block means you will be reading a chunk of data at a time. For example, from hard disk you are not going to read 1 byte at a time, you are going to read 1024 bytes at a time. So that's called block device. Okay, so all that you have to do is you just say here my hard disk and say B and give some number like 1000. You are free to give any number. Only thing, this major minor numbers you have to use it in the device driver program that you write to map this device file with that driver. Okay. So here again if I do ls here, you see now it is a block device file. You will see your letter B here.
So if I'm having multiple devices, right, maybe that 1000 would still remain constant, right?
Yeah, 1000 will remain constant, and then this will be 6, 7 like. Now, why this is done is you have only one device driver for the hard disk, and hard disk can have different file systems. One may be using ext2, one may be using ext3, or one may be using proc file system. So why have different drivers for each file system? You have only one device driver, and minor number will decide which file system you are interacting with.
Okay.
Now you need to look at different file systems that are commonly used. A decade back or so we had ext2 file system. Now it is not used. Then that was extended or enhanced with ext3 file system, and what we have today is ext4 file system. Now what are these different file system and how do they work? Okay, so there is a feature called a journaling. What is that journaling? We shall see quickly. This was not supported in ext2, and whenever you are in the middle of read write on the disk, and if the system stops or crashes, then recovering that file was very difficult. So the journaling feature was introduced to recover the file if whenever a system crash happens when you are in the middle of read write. So ext3 brought in that journaling feature, and it is also there in ext4. Now reliability part, that is whenever system crash happens, then a full scan has to be done. So this is very time consuming and also slow, and reliability in ext3 is enhanced to some extent, it's medium, and in ext4 it is very high. And if you see the performance of the file systems, since there is no journaling which is an overhead, so it is fast. So ext3 is slower and ext4 is faster than ext3. And there is a maximum file size you can store is limited to 2 TB in each of these, whereas in ext4 it is enhanced to 16 TB. So one file when you create it can be of size 16 terabytes. Then the maximum file system size, it was limited to 32 TB in these two, but in ext4 it is extended to 1 exabyte. Okay, I don't know how many times it is in terabytes. So that is a enhancement in entire file system size. Okay. So file allocation is done, block mapping in these two, and there is a different technology employed, events extents. This I have not gone into the details, but maybe a better one compared to the block mapping. Now, if whenever file crash happens, you have to run a command called as fsck, okay, file system check. So this is very time consuming in ext2, and it's very low in ext4. and compatibility is that all ext4 is backward compatible with ext3. So whether it is used today or not, ext2 is very rare, limited, and most common. So you can take it for granted, but today any Linux operating system you take, the file system employed is ext4. Okay. So knowing little bit about what file system you are using, you know what are the capabilities of that file system and which one to use in given scenario. Now the journaling part which I was referring to, journaling is nothing but before you write to the actual file system, you write all the changes into a log file. That log file itself is called as a journal. Okay. So application, when you perform write operation, you first write the data into a log file, commit that log file, and then go to update the file system. The reason why it is done like this is that in case if there is a crash, then you can just take the log file content and write to the file system when the file system comes up again. Okay, so this is the sequence that is given here. So whenever you do a file write or whenever you create a file, there will be a journal corresponding to each file. So when you make changes to the file, you first write them to the journal and commit the changes. After you have done the commit, then you go to update the actual file system. That is the inode table, directory blocks, data blocks, these are all updated. And then clear the journal. The content of the journal is cleared off. Why this has to be done is that in case of a power failure or the disk system failure, there is a data in the journal which you can employ to update the file system later. So the recovery is very fast in ext4 file system because of this journaling feature. Okay. So you must be aware of these things. Okay. Now having learnt about the files, I wanted to take you to networking basics. So sometime in your undergraduate you have learned about computer networks. What is networking and why do you need to have inter-process communication between processes and all that. So networking is basically connecting two or more machines for sharing the system resources. Like I want to transfer a file from one other machine to my machine. So if you have a network, then I can connect to that machine and request for the file. So if you have the permissions to read the file, you will be served with that file. And normally they employ client server model. Okay. And this client server model can work on two modes. One is request response mode, the other one is streaming. Request response means you first send a request and there will be a server will respond accordingly. In streaming, you connect once, and once you connect, you start getting stream of data, and the client has to read this data and process it in real time. Okay, so there will not be many request responses here. You only connect once, first time the request is made, and then continuously data starts flowing from the server. Okay. Now to make networking possible, we employ what is called as a TCP/IP protocol stack. Now this is a software layer which is present in every machine, even in switches and routers. This protocol stack will be present, and some part of this will be used in the host machines, in the routers, and also in the switches. So which part works in which device is decided by what is the role of that device. So why there are 4 layers that are employed? Why not we have just one layer and you do everything? Now networking, as you all know, it's a very complex task. Okay. So first thing is you have to establish a connection. You should identify which host on the network you want to communicate. And during you must do a handshake before you start sending and receiving the data. And while you send data, some of the data packets may be lost and some data packets may be corrupted, and also you must know on which path you have to send so that it encounters minimum traffic on its way. So all that has to be done by the the software. And if it is a layered approach, then building the software and maintaining it and extending it becomes easier. So that is why we have a 4-layer protocol stack. As you can see here in this diagram, at the bottom it is a data link layer, and then this data link layer interacts with the actual hardware, that is the Ethernet card, and deals with all the low level details of how data has to be communicated using physical addresses. So there is a address called as MAC address. Similarly, at the lowest level, if any errors occur, error correction features are built into. So this is the functioning of the data link layer. On the network layer, this will decide how the routing of the packets has to be done. Okay, so which algorithm it must use to route the packet so that it encounters minimum traffic on its way. Transport layer decides how the data has to be broken down into different packets, and each packet is assigned with sender's address and receiver's address, and whether to employ a connection oriented protocol or connectionless oriented protocol. So there is a TCP and UDP. There are two approaches. If you employ TCP, which is connection oriented, it is reliable. That is, whenever you send a data packet, it is ensured that the data packet will be delivered to the destination irrespective of data loss or packet loss, anything. If packet doesn't reach the destination, it will be resent. Whereas in UDP, which is unreliable, you just send the packet hoping that it will reach the destination. No guarantee that the packet will actually reach the destination. Now, what all might be wondering, if it is not reliable, why are you employing it? In certain applications like video streaming, 1 or 2 packet lost is not a problem, because the eye cannot detect the loss of few packets. Whereas if it is a email, every packet has to be reliably sent. Otherwise, when you receive an email, some part of it is missing, you will not be able to make out the actual meaning of the message that you receive. So connection oriented is suitable where the entirety of the data is important. So like email or file transfer protocol, etc., TCP is used. Whereas if it is audio and video, you always employ UDP. The reason is in UDP, speed is important. So it is much faster than TCP. See, in video processing or video transfer of data over the net, faster delivery is more important than the reliable delivery, because in real time the video has to be played. For that, speed is important. If 1 or 2 packets are lost here and there, then that is fine. So UDP normally employed in audio video, whereas TCP is employed in all text-based data transfers. So that you must be aware of. And whenever you want to do network programming on Unix platform, you must be aware that there is a range of IP addresses that are assigned to the machines. Okay, so as you know, IP address is a 32-bit number. So this 32-bit number is very meaningfully split based on what type of or what category of network you are dealing with. So there is a class A address which starts from 0 and goes up to 127.255.255 like this. And this address has two parts, host address and network address. As you can see, there is a net ID and host ID. So here, if you have less number of networks and more number of hosts on it, then you must use class A address. Okay. Then if it is a medium level, then you use 128-bit for the network address and remaining for host addresses. So you will use 16 bits for network ID and 16 bits for host ID. But if you have a large number of networks and only small number of hosts, then you go to class C. That is, you have a wide range of network IDs, that is starting from 192 to 223. Okay, and then the host can be 255. So smaller networks Okay, number of hosts will be less, only 255 in a network, whereas there will be large number of networks, and the networks are identified with this 12-bit number, sorry, 24-bit number. Then in class D, the range starts from 224 to 239. Okay, so here only hosts are used. No networking is possible in class D. So this is mainly for multicast addressing. And there is a class E, which is undefined. Okay. So normally we'll be working with class C addresses because in your organization or in colleges, the number of hosts will be limited, and class C is the most preferred address. And whenever you print the IP address, you will see that it is starting with 192 up to 223. Okay. Now, if you look at the inter-process communication using sockets, you need to understand this concept first, that what is a socket. So socket is file-like endpoint for network communication. Okay, so it will also return a descriptor, and you can perform read-write operation. So let me explain what a socket is. Imagine that you have a process here. Okay, so this process has its own instructions to execute, and this is the machine. We call it as host, and this host is identified its IP address. Let's say 192.169.1.1, something like this. This is the IP address of this host, and this is the socket, that is the endpoint for communication. And this endpoint is identified with what is called as a port number. Let us say this is the process which is running a web server. Normally web server uses port number 80. Okay, so you create an endpoint and connect this endpoint to the process. And this is another process in another machine. So this is process. This is host 1, let us say, and it has its own IP address 192.169.1.2 like this. This is host 2. This will also have a socket, and it can use some port number like 3000, and this process also need to bind to this port number. Now the communication between the two machines will take place through these endpoints. Okay, so why this arrangement is done, that you have a socket endpoint and the port number? The reason is on a single machine there can be more than one process running. You could have one more process here, and this, if it wants to behave like a server, let's say file transfer protocol, it will serve the files that you request, then this will set up its own socket, and the port number will be, let us say, 23 or something. Anybody who wants to connect to this file transfer server, is that it has to connect to this port, not to this port. This is only for web server. So if this process, let us say this is your browser. So on the browser, whenever you see a localhost / some IP address / test.html, that will connect to this port number 80, and this port number, anything that comes on port number 80 will be delivered to this process. This will check what is the file name that is requested. Okay, so it will check on the hard disk, is there a file called as test.html? If yes, it will read the entire file and then transfer it back to this process, and this process will render it in your browser. Okay, so this is the communication that will be happening. Okay. Now, how do I create this socket, and what all steps I have to follow to build a server or a client? Okay, so we'll see subsequently a simple program where I'll build a server and also build a client and connect them to perform some basic operation. You can build what is called as a echo server. If I say hello to the echo server, it will again send back the same message, and you can see that message coming back from the server. Now there are some 6 steps that you need to follow to build any server or a client. So first step is create a socket. Second step is bind it to the port. Then wait for the client request to arrive. So there is the listen API. Once the request has come, you can accept the connection and then perform read write. And once you are done with all the read writes, you can close the connection. Okay. Similarly, on the client side, you require fewer than these steps. You only have to create a socket, connect to that socket, perform read write and close. Okay. So these are the 4 steps. See, if I'm using connection less and connection oriented, then I'll be choosing appropriate protocols. Now, before you understand how to write the code to build a client server, you need to understand a socket structure that is used. Now, there is a structure called as sock addressing. It contains many subparts. Now, here SYN refers to socket internet address. It's for internet family. So SYN family, SYN port. The SYN here refers to socket internet. Now what is the length of the entire structure is stored here. Then socket family. This refers to address family INET. If I write like this, it will be using IPv4. You are aware that internet protocol uses 2 addresses, IPv4 or IPv6. IPv4 is 32-bit, whereas this is 128-bit. So if I just write AF INET, it will use 32-bit, and if I say INET 6, then it will use 128-bit. Then this is where the port number has to be specified. For example, if I am building a web server, then this has to be 80. And if you are building a eco server, you can make it 8000 or 9000, whatever. So there is a range of port numbers which you can use. There are some reserved port numbers also. Okay. So port number 21 is for SMTP, port number 23 is for file transport, port number 80 is for web server, port number 29 is for DNS. So you should know what are the reserved port numbers. You should not be using them if you are building your own test server like eco server or something. But anything beyond 8000 you can make use easily without any clash with these reserved port numbers. And this is where you have to specify the IP address of your host where you are building the server or trying to run the server. Okay, so you can address a specific port IP address like 169.1.1, and you also have an option to specify in address any. Okay, so any address that comes, because the address is set by the DHCP server. So you may have to have one Ethernet card, and that address is fixed. Okay, you don't have much freedom. You don't have to go and check what is the IP address of your machine and plug in here. You just say in address in. Whatever is the IP address that is assigned by the DHCP server, that IP address will be automatically made use here. And this is a large structure, and some bits are not required. You can make them 0. So only these 4 parts are made use. Okay, and the remaining part is 0. If you look at the structure here, actually it is a 16 byte structure, of which first 2 bytes are used for family. That is, if you look at sock address in here, 2 bytes are for defining AF INET, family. This is 2 bytes for the port number and 4 bytes for the IP address, 4 or 6 depending on whether it is IP4 or IP6. And as you can see, the last 8 bits are made 0 because these are not required if you are using internet family. These are used for some other type of address family, like there is one IRDA, infrared address family, where these remaining bytes are made use. Okay, so the same structure is helpful in building communication between two devices, either using Ethernet or infrared or Bluetooth. Okay, depending on what communication medium you are using, these bits are made use accordingly. So for our purpose, we'll be setting these 8 bytes to 0. Okay. So having understood the basics of socket programming, let us look at the 6 steps that we have to perform on the server side with the sockets. So if I just open up this sock.c. Okay, so first step is create a socket. Of course, you have to include some header files like arpa/inet.h. So this contains the description of the socket API and all the socket structures that I am using here. So whenever you create a socket, the first part indicate what is the address family that you want to use. So it is AF inet. I am using IPv4. And whether you are using TCP mode of communication or UDP mode of communication, that is decided by the second argument. So if I say sock stream, then I am using connection oriented reliable protocol. I am using connection oriented, which is reliable. Now if I want to use UDP, which is connectionless and unreliable, then you have to change it to dgram. Okay, so just by one change you are indicating what way of communication you are using between client and server. Dgram is UDP, which is connectionless and unreliable way of protocol, which is suitable for video transfer or audio transfer. But since I want to build eco server, I just want it to be stream. This is a TCP mode of communication, so you can label it as TCP. And then you have to fill one socket structure address. So I told you sock address in is a structure again which has many subparts. So first is again SYN family, which is AF inet. Port number, this is where I am using 8080. Now I am using one library function as HTONS. It stands for host to network short. Now machines may use big endian notation or little endian notation. Are you aware about big endian and little endian? Hello?
No, sir.
Now this is because you know that machine stores data in the memory, 1 byte at a location. Okay, so let's say you have memory starting at 8000. This stores 1 byte and next byte will be stored at next address. Just a minute. $8,001, let us say. Now this 8080 you have to store in these two memory locations. Now what might happen is since both is 8080 is not a problem. Suppose if it is 8089 like this. Okay, now if it is a big endian, then in this 8000 you might store 89 here, and in the next location you might store 80. Okay, let's say this is big endian notation. That is upper byte in the upper address. But when you send this IP address to another machine, which is required at the other end so that it recognizes which machine it is communicating, it might be using little endian. It might store in the lower address higher byte, that is, it might store 80 and 89 here. So then there is a problem. That is, the client is thinking that the server is at location 8980, but actually it is at 8089. Now how do I solve this problem? Okay, so what is done is, there is a standard maintained that on the network it is always big endian. That is, you will have 80 here and 89 here. That is higher address on the higher byte on the higher address. So you have to convert. Suppose you are on a little endian machine. You call this function STONS, host to network short. That is, this will be converted into big endian notation and it is sent. And if the client is big endian, it will take it as it is. But if it is little endian, it knows how to convert this into little endian at the receiving end. So always on the network it is big endian. Okay, and that is why you have to use this function STONS before you assign it to the port. And then the actual IP address, if I know, I can plug in that IP address. But if you don't know what is the IP address assigned to you, then you just say in address any. So it will go to the lower layer of the protocol stack and find out what is the IP address that is assigned to your machine and use it here. So first step is create a socket, initialize this socket structure, and then bind this socket to this socket structure. As you can see here, the second step is bind the process to the socket. So there is a function called as bind. So whatever S that is received after socket is nothing but socket descriptor. So just as you receive a file descriptor, what you receive after you create a socket is called as a socket descriptor. If you want to name it as S, it is okay. You can, if you want to name it as SD, that is also fine, socket descriptor. And that is what is made use in this bind. And then bind the IP address and the port number to the socket using this bind function. And before you supply this address, which is initialized here, you have to typecast it appropriately, sock address star, so that it knows exactly how to interpret these different parts. And then specify the actual size of this address. Okay, so the size of is made use. Once the binding happens, you have to wait for the connections to arrive. So there is a listen API. Listen S, 1. Now how many requests you want to queue up, you can decide here. If I say 5, it can receive 5 requests and put them in the queue. And if you have only 1, you can put only 1 request, and other requests, when they come, you can drop them. So normally it is a number between 1 and 5. Okay, so it depends. You can specify any number here, but normally it is 1 to 5. So 5 requests will be pending, and if you want to choose one which has come first, then you have to call accept API from the same socket, and this will give you the client side descriptor. This is again a number corresponds to the client side. Of course, there are 2 more arguments here. These you can use to receive the client IP address and other details. So for the current scenario, that is simple echo server, these are not required, so you can put them null. And what is received from the client, if you want to store, you can define a buffer like this, assuming that the message sent by the client is limited to 1024 bytes. Now, if you observe, you can just perform a read operation just as you would read from a file. You are reading from the client socket now. So read C into the buffer the number of byte received. So keep on doing this until all bytes from the client are read. So if you recall, when we read from the file, we were having this while loop. So that is exactly similar to reading from a file. So as you can see, I am reading from the socket of the client and performing a write operations. Whatever is read is returned back to the client. So this is mimicking a echo server. And the last step is close the sockets so that all the system resources which are held up for maintaining the sockets and all the data transfer that is taking place is all released back to the system. Close the client socket and also the server socket and return. Okay, so these 6-7 steps you have to perform when you want to do socket programming. Okay, so have you got some idea as to what is a socket and how to initialize the socket structure and how to do the binding and accepting the connection and perform read write? Any doubts here?
Yes. So in the exit, right, the car buffer
Pardon?
in the accept request.
Okay, accept, yeah.
There after accept you're doing the car buffer.
No, accept will accept the connection which are queued up in the server side queue. When you say listen, a queue is created.
After accept queue కూడా
1 minute. Yeah.
what is the next step, sir?
After accept,
Yeah.
yeah, you declare one.
The buffer range.
Yeah. Buffer is just memory that where the data received will be stored. Since it's a echo server, you'll be typing some message, hello world or something. So to hold that message, you are declaring one buffer which is of type character, and you are performing read write, reading from the client and writing back to the client.
Is that also static?
Pardon?
Is that also static determining the size of the buffer?
No, you decide. This is static now. Okay, you decide how many bytes you want to reserve. Let's say you are only sending one small message like hello world or something like that. You can limit it to 50 also.
Okay. Or size of buffer will give the actual.
Size of buffer will give you actual buffer size that you are passing here.
Okay.
But number of bytes read will be returned by this read option. As long as this is more than 0, it means there is enough data which is coming from the client side. You keep reading and keep writing to the client. Okay, of course you have to write a client process also, like the way I have written the server here, which we shall take up in the next class. But what I want you to understand is different steps that are involved in building a server side. Okay.
Yes, this is clear.
This is clear, right? Okay. So if you run the program, nothing will happen. It will just run and close. Okay, because the client will not be. If I compile this, it will wait for the connections to arrive. Sock.c. Of course, I have to. I have to remove all this, otherwise it will throw errors. TCC sock.c minus server dot less server. So it will get blocked here. It is listening for the client connections to happen. I have to write a client in another terminal and run it and then say uh, client like this and they say hello world. Of course, I have to write this program. When I do this, actually you will see the message received by the server and server will respond back to the client, and in this terminal you will see hello world coming back again. We shall
Okay,
see
sir.
that actual implementation of client and running of client server both in my next session.
Okay. Okay. Please
Please
share
share
this
this
code,
code,
sir.
sir.
Yeah, I'll share this code and you please go through and be acquainted with the syntax, and next time I'll demonstrate to you the actual client server communication. All right?
Yeah.
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 Okay.
Yes,
Okay,
sir.
sir.
We'll close then.